Hello, this is Professor Kuehn, and welcome back to my lectures on space, time, and motion, where we are beginning to look at Einstein's theory of special relativity. You might remember in my introduction to this, I mentioned that Einstein published his special theory of relativity, which is his new theory of space and time, back in 1905. He later published what has come to be known as his general theory of relativity in 1916. And what we are going to be doing is focusing on his special theory of relativity, but we may make mention of his general theory of relativity now and then as occasion arises. Let me begin by saying this. Things appear differently to different observers. So you might think about, for example, a table. I'm going to draw a picture of a table. A rather simple table. Okay, and the point is that the tabletop may appear different to different people. So if one were to look at it from above, so if this is your eye looking down at it, then you would see it to be a square. But if you were to look at it instead from the side at the tabletop, then you would see a long, narrow rectangle. This is no surprise to you. This is really non-controversial. It was a point that was made, for example, by Descartes in the 17th century in his Meditations on First Philosophy. So the question that you might ask is, which of these two observations, the tabletop being square or the tabletop being a rectangle, is correct? Well, of course, the answer is both. Both are correct. It appears different to different observers depending on their point of view, depending on their perspective, you might say. This is not just true of tabletops, it's true for many different things, and it's the case for reports of events. So for example, the scene of a crime may be reported differently by different witnesses who assess the events relating to the crime from different perspectives. They could maybe say different things without necessarily contradicting one another. In fact, if all the stories of the witnesses were identical, they would perhaps be even less trustworthy because you would suspect that they had talked about and colluded to make stories that were exactly like each other. So the very fact that the stories are slightly different and yet not inconsistent lends credibility to the accounts of the witnesses. Now, let's think about another example. Let's think about the case of the description of motion. And here we're going to be getting closer to the topic at hand, the theory of relativity. So let's suppose that we were to have someone riding in a train. So I'm going to draw a picture of a train. And let's draw a person in here. This will just be a stick person. I don't want to spend a lot of time drawing it. And let's suppose that they have a ball. And this is the box of a train, and I know we're standing on the outside, and trains are, typically made of opaque material. You can't see inside. So let's just, to make things easy, say the side of the train is made of a glass window, so you can see through it. You can see what's happening inside of it. Okay? And let's suppose that there's another person standing outside of the train, watching the train go by. Let's call this person John, and let's call this person Luke. Now, what do I want to say? I want to point out the following fact. Let's suppose that Luke were to drop his ball, and we wanted to describe the trajectory of that ball from two different perspectives. From the perspective of Luke, who's riding in the train, and from the perspective of John, who is outside of the train. So what we might do is, from Luke's perspective, perhaps we would draw a coordinate system. Maybe the x-axis would correspond to the floor of the train, and perhaps the y-axis would correspond to the axis along which the ball is falling. So if you were to drop this ball, here's the ball right here, if you were to drop it, how would Luke describe the trajectory? He would say, well, the ball is falling straight down within the train. So this would be the trajectory of the dropped ball, according to Luke. Now, and this is an important point, let's suppose the train were in motion with some speed. I'm just going to call the speed u. You might think of this as 60 miles per hour. If the train was moving at 60 miles per hour along very straight, smooth tracks, it would seem to him as if he wasn't even moving. Perhaps you've experienced this when you're riding in a train or maybe in a car that's moving at a very fast rate but along a smooth road, or if you're riding in an airplane. When you drop something in the airplane, it seems to fall exactly straight down from your perspective. It's not like if you're pouring cereal on milk onto a bowl of cereal in an airplane, it's going to fly back in some funny direction. No, it falls straight down into the cereal bowl, just like if you were sitting at home in your breakfast room. So, in other words, if Luke drops this ball, although the train is moving at a high speed, provided it's a very smooth ride, from his perspective, he will still describe the trajectory of the ball as being straight down along the y-axis. But what about John? How does he report the descent of Luke's ball? Well, he would also perhaps describe it using a coordinate system. He is going to have his own axes. We'll call these maybe x prime and y prime to indicate that they're a different set of coordinates. And maybe the x-axis for him also corresponds to the bottom of the train, and the y-axis, maybe it corresponds to the location of the ball at the moment that Luke drops it. So from John's perspective, he sees the ball at the beginning right here along the y-axis, but then when Luke drops it, because the train is moving forward and hence the ball is moving forward, the ball is going to follow this trajectory, kind of a trajectory like this. It's going to follow a parabolic trajectory as it falls. So this would be the trajectory of the dropped ball according to John. Okay, so once again, Luke on the train reports a linear trajectory of the dropped ball, whereas John, watching the train race past at speed u, reports a parabolic trajectory of the dropped ball. Now, here's the question I want to ask. Which of these observers sees the true trajectory of the ball? And your answer to this question might depend on whether or not you believe there is an absolute frame of reference or absolute space. Remember, we came across this idea in the work of Newton. One might say, well, if there is no such thing as absolute space, then there really is no way of knowing which is the true trajectory of the ball. They're both describing equally valid trajectories of the ball. If, however, you believe that there is some absolute reference frame, you might say that, well, Luke sees it falling straight down, John sees it moving in parabolic motion, but John is the preferred reference frame. He's the one really at rest, and so his is really the correct trajectory, and Luke's is just an apparent trajectory for Luke. Einstein, in his theory of relativity, is going to argue that both of these are equally valid frames of reference, or equally valid descriptions. Why is that? Because Einstein is going to argue that there is no preferred or absolute frame of reference. Both of these observers, Luke and John, can consider their own frame of reference as being valid, and there's no way of distinguishing which one is better than the other. That's one of the main points that he's going to be making in his theory of relativity. One other thing that I want to point out about this is notice that Newton's laws of motion are obeyed for the ball according to both of these observers. So Luke says, when I drop this ball on the train, it falls straight down. Why is that? Because there's gravity pulling on it and it follows a straight down trajectory from my frame of reference. John, on the other hand, will say it also is obeying Newton's law of gravity, it just has different initial conditions. Yes, it falls down because of gravity, but it has a horizontal speed, a bit like a projectile being launched horizontally. So why do we see it moving in a parabolic trajectory? Because we're compounding a uniform horizontal motion with a naturally accelerated vertical motion. So according to both of these observers, the ball obeys Newton's laws of motion. Okay, let me pause there, and I'll go on in the next lecture to talk about the principle of relativity.